The previous exercise demonstrated that it is fairly simple and straightforward to compare a sample average to that of a known standard. For example, blood pressure, where the blood pressure is known. However, there are many cases where there isn't a defined standard to compare a value against. And in that particular instance, we need not only a treatment value, but also a control average as well. In the spreadsheet in front of us, I've replicated some control values. So we have 10 control values, we have 10 drug values, and we have a mean for the control. I had a look at this mean for the control in the previous exercise, but I've also got a mean for these 10 drugs as well across the row. And finally, I have a difference here. So this value of 8.5 is equal to the mean for the control, 120.74, minus the mean for the drug, 108.88. And I've copied this function all the way down for all 1,000 of the rows that I've used in the spreadsheet. If we draw up a histogram of this difference between the mean and the drug, we see something which is very simple and straightforward. Firstly, we get a nice smooth bell-shaped curve. Secondly, the thick black line I've put in, which is the mean value for the difference, is centered on the true mean difference between the control and the drug treatment. You can see that I fitted a nice smooth bell-shaped curve to this, and I've used the standard deviation of this distribution to put in my red line cutting off 95% of our values to the right of this line and 5% of the values in the tail, so a one-tailed test. And I have a sample size of 1,000. The thing that we're comparing our average value against is this line here for 0, which says there is no difference between the treatment and the control. As you can see, this is well into the tail of the graph, well to the left of the red line. So there is a real difference for our sample here. In order to calculate this red line, I was basing it on the standard deviation of this distribution. And you should know that when you come to have a look at the two-sample t-test, that there are two different ways of working out the statistical significance. The reason for this is because there are actually two different ways of computing a standard deviation for this graph here. One of the ways of computing the standard deviation assumes that the standard deviation of the control and the standard deviation of the drug treatment are the same, or can be assumed to be the same. One of them doesn't make that assumption. It assumes that they are different, that you have, when you draw up a histogram of the control peak and the drug peak, that you have one thin peak and you have one fat peak. They're not the same width. And these can lead to slightly different estimates of the standard deviation of this histogram of differences in means between the control and the drug. So when you get to your SPSS output, you'll find that there are two rows in your output when you're looking at the significance, and you have to be able to choose the correct one. Which one you choose is based on the Levene's test of significance to tell whether the two peaks were really the same fatness or not.